Так, ну вы получаете же рассылку, да? Как-то не получается сообщения не по рассылке не получаете? Никакие? Ну, когда я пишу, например, что вот там, ну, например, то, что, не знаю, там, что записки лекций обновлены, вы получаете сообщение? Нет? А, так вообще знаете, где сайт есть?
Да, я знаю, и записки лекций, уже домашки отправляешь, я там беру. Это все я знаю.
Да. Да, получается, что вы не добавлены в группу, получается, странно. Ну ладно. Okay. So we want to prove Riemann-Roch theorem. Okay, so I recall that that from last time, from last lecture. That if X is paracompact topological space, and we have a short exact sequence of sheaves, then we constructed exact sequence of group homomorphisms Okay. Yes. Yeah. Basically, using this sequence is one of the main tools to compute cohomology groups of sheaves. Yes. So actually, often, people just use just the existence of the sequence without precise description of these homomorphisms. Okay. Okay, then we want to prove a Riemann-Roch theorem. So for a compact Riemann surface and the divisor D, then the cohomology groups of this sheaf are finite dimensional, have dimension and yes. Okay. Yeah, the proof is the following. So we yes, recall that if so take take any p, then recall that we introduced as the skyscraper sheaf. Skyscraper sheaf CP. So we introduced it at some moment, but I recall, so CP of U is equal to 0 if U does not contain the point P, and C if U. Где? Здесь? Ну, вообще, иначе это пространство не будет конечномерным. Ну, если вы возьмете вон c, да, то, ну, как множество мироморфных функций, ну, голоморфных функций на c, ну, бесконечномерно. Yeah, so take, then we have the skyscraper sheaf. Then, okay. Then we will use yeah, so 2p we assign the divisor on x that the divisor d, okay, oh, d, okay, the divisor on x that has a value 1 at p and 0 otherwise. Denote it also by p. Denote by p. Yeah, so by a point, yeah, so if we have our Riemann surface and have a point, then we also denote by the same letter the divisor, so meaning the function on our Riemann surface that has a value 1 at p and 0 at other points. Yes. Okay. Then ну, это определение, сейчас вы, видимо, говорите про определение порядка нуля, как бы. Ну, порядка там зануления мироморфной функции точки, ну а при чем здесь это? Я пробую, ну... Ну хорошо, ну смотрите. Ну просто мы определим define dp by dp of x if 0 otherwise. Denote p dp. Yeah, formally speaking, we construct a function that takes value 1 at x, at p, and 0 otherwise. And we just this is a common notation that we denote this divisor by the same letter p. So nothing clever here. Okay, then then yeah, obviously minus d p minus d of x is greater or equal then minus d plus p of x. So it means that O d of u is included in O d plus p of u for any open set in X. Yeah, just by definition, yeah, of this. This gives I want to check whether I want to use any notation for this inclusion. No. Okay, so this gives a sheaf homomorphism O d plus p. Yeah, such that this sequence is exact. Yeah. Is exact. Где? Ну, мы здесь не рассматриваем структуру алгебры, мы рассматриваем просто структуру векторного пространства. Вот. То есть, ну, умножение на константы и сложение. Yeah, actually, it was a bit funny to check the exam because just regarding problem 3. Recall that it was some simple problem about OD, about sheaves OD, and actually several people they used some Cartier divisors, so they used actually completely different definition of these guys. So okay, so clearly these people did not come to my lecture, just read some other books. Okay. Где умножение? Повторите еще раз, я не пропустил, у нас сначала. Да. На функцию. Не очень зачем вы говорите образующий главного дивизора. Мы говорим то, что разность d минус d' это есть главный дивизор, то есть дивизор какой-то функции f. Ну, вот мы на эту функцию умножаем. Кого? Функции? Ну, можно, конечно, складывать, но по порядке как бы плохо при этом себя ведут. Где? Где структура алгебры? Ну как, ну если вы прям уж хотите структуру алгебры, да, это пучок алгебры над структурным пучком, как бы. Ну нам это не надо, как бы. Не, ну не, ну да, там можно, ну да, можно складывать. Умножать на на голоморфные функции. Да. Okay, so this gives you sheaf homomorphism. So let us extend it. Let us extend this to an exact sequence yeah. So what we do, choose a coordinate a chart VZ around P. Ну как, это же вложение просто. Ну, да. Просто под пучок, вложение. Choose a coordinate chart around P, such that Z of P is equal to 0. And then, so for, so, define define a sheaf homomorphism. Я еще же не ввел, то есть как бы я говорю, давайте вот ее построим сейчас. Я сейчас буду строить этот гомоморфизм. А? Да. Define a sheaf homomorphism. O D plus P to CP as follows. If take take some open set and F in O D plus P of U. Then if U does not contain P, so define a sheaf homomorphism beta. Define a sheaf homomorphism as follows. Take U and F. So if this point does not contain this set, then beta of F is equal to 0, which is an element in CP of U, which is 0. If U contains P, then then F has a Laurent series expansion around P. So F is equal to sum sum I greater or equal to minus K minus 1 Ci Z to the power I, where K, we just denote by K D of X of P. So if this point belongs to our set, then we consider Laurent series expansion and define beta of F by C minus K minus 1, which is a complex number. So which is a complex number, and which is C, and we know that CP of U is the space of just the space of complex numbers. Yes. So very simple. We take an element in OD plus P of U. If U doesn't contain P, then we just define the image to be 0, and then if this set U contains P, then we take Laurent series expansion of F and take the coefficient of Z to the power minus K minus 1. Yes. Then actually I claim that it is very easy. So obviously this sequence is exact. Is it is it clear? Yes. Yeah. So clearly the composition here from OD to OD plus P and here is 0. Yeah, because if we have a function from here, then it has a pole of order k or smaller. So this coefficient will be automatically 0. So this composition is 0. Yeah. Ну, потому что это же мироморфные функции. Ну, по определению этого пучка, сечение этого пучка — это мироморфные функции. And then so here, so just by definition, so if a function from here goes to 0 here, then this exactly means that it doesn't have a pole of order k plus 1 at this point, so it belongs to here. So yeah, and then surjectivity is also obvious. Yeah, so I guess hope it's clear. Yeah, so this sequence is exact. So we have the exact cohomology sequence. Cohomology sequence. Sequence 0 H 0 X O D H 0 X O D plus P. Okay, and the H0 of this sheaf. So the space. What is H0 of CP? What is the H0? It's 0x CP. What is it? C. Yes. This is C. Then we go to H1 XOD H1 XOD plus P H1 X CP. Okay. Yeah. Then what is this? What is this? What is H1 X CP? So how do you think? Yes. To be honest, I don't remember. I don't think so. Yes. So lemma H1 XCP is equal to 0. Proof. So take omega in H1 X CP. Take omega X CP. And it's representative. and some f in Z1 U P such that the class of f is equal to omega. Yes. And then you just what you do. Then for every take yes, then for every x in X, take a neighborhood Vx of X such that Vx is in UI for some I. So U, as usual, U is an open covering indexed by some set, such that Vx is in UI for some I, and Vx does not contain P for if X is not equal to P. Yeah. So yeah, the picture is very simple. So you have your Riemann surface X, your point P. Then yeah, you have some open covering. Yes, maybe. And then you do the following. So for any point X, you take some neighborhood that is inside some UI, and then if moreover, if X is not equal to P, you just take it small enough such that it doesn't contain P. Yeah. Yeah, and then okay, Vx in UI for some I, so you can then define phi of X is equal to I. Yeah, so phi is the function from X to I. Well, you get the function from X to I. Yeah, so then then of course then you get then just by definition you can restrict then да, ну это refining map. Then if we denote V just discovering Vx and then you get that by construction this open covering is a refinement of U, and of course the class then of course the class of the restriction of F is equal to the class of of F is equal to omega. Ну, я же говорю про компактность, но это многообразие, оно все выполняется. Ну, про компактность это свойство не покрытия, а топологического пространства. Вот. ну, что у каждого покрытия есть локальная конечность под покрытие. Это свойство пространства. Ну, это такое очень мягкое свойство. То есть, ну, все многообразие, например, ему удовлетворяет симметрические пространства. То есть там есть такое довольно общее утверждение, что любое локально компактное пространство со счетной топологией паракомпакт. Ну, в общем, это надо постараться, чтобы придумать не паракомпактное пространство. Okay. So the restriction of course, of f to v, its class is equal to f, of course, by definition of cohomology. But then, okay, know that this guy this guy belongs to Z1 of V CP. But then note that that Vx intersected with Vy, it doesn't contain P for x not equal to y, and this implies that Cp of Cp of Vx is equal to 0 for x not equal to y. And this implies that the group of cocycles of this covering is 0 with respect to this sheaf is 0. And this implies that f is 0, and so omega is 0. And so the cohomology is 0. Sorry? Because what you get that f, that your restriction of, okay, so you want to consider this group Z1 of VCP. So you take any element in Z1 VCP. Actually, and we know the description of we know the description of the space of cocycles. So it's what is it's gxy, where gxy is in Cp of Vx intersected with Vy. Yes, and then you know that Gxy should be equal to minus Gyx. Yes, but then of course, I mean, then if x is equal to y, then automatically Gxx is equal to 0. Yes, and then, I mean, if x is not equal to y, then Gxy is equal to 0 by this. Yes. So you get that this group, this space of one cocycles is 0. So the first cohomology group is 0. Yeah, so this proves. Okay. Any more questions? Is it fine? Yeah? Okay. Okay, and then we can, yes. Yeah, so we proved the lemma. Yeah, so we obtain an exact sequence, the exact sequence of vector space homomorphisms, of vector space homomorphisms. So 0 H0 XOD H0 XOD plus P C H0 H1 XOD H1 XOD plus P 0. Yes. Yeah, and then you can denote this by beta. Yeah, 0. Then what you then you get I mean yeah, then actually we get two short exact sequences. So we get two short this is a standard way. A long exact sequence can be splitted in short exact sequence. So the first one you write XOD and then you take the image of beta 0 the image and another one you can take 0 then the C quotient by the image of beta 0 H1 D 1 X O D plus P. Yes? Yeah, so yeah, so first of all, so what you get? You get that if so you get that that the dimension of hi x OD is less than infinity for I equals 0, 1. So this is equivalent to the fact that the dimension hi x OD plus P less than infinity. Yeah, so it immediately, so because you see, if this space is finite dimensional, then automatically this space is finite dimensional. And yeah, if this space is finite dimensional, then this space is finite dimensional. And conversely, if this is finite dimensional, then this is finite dimensional. And if this is finite dimensional, then this is finite dimensional. So, почему если это конечно, то это конечно? Ну а как? Ну у вас же здесь фактор. У вас есть пространство, у которого подпространство конечный фактор. Пространство конечное. Ну что, и все пространство конечно, мерно. Ну да, ну это же образ, он в C лежит. То есть вот этот образ, он у этого, как бы у этой штуки, да, размерность is equal to 0 or 1. Yeah. Okay. So, and Yeah, so, and yes, and if one of this is true, and if one of this is true, and if one of this is true, then what you write? You write that dimension. You write the equality of dimensions. Yeah, dimension of H0 x O d plus p is equal to dimension H0 x O d plus the dimension of the image of beta 0. And from the second, you get that the dimension H1 of x O d is equal to the dimension of C quotient by the image of beta 0 plus dimension H1 x O d plus p. Then we sum and get that here you get dimension H0 x O d plus p plus dimension H1 x O d is equal to, yeah, and then first of all, dimension of the image plus the dimension of the quotient of C by the image, so this is 1. Plus dimension H0 x O d plus dimension H1 x O d plus p. So you get that dimension H0 x O d plus p minus dimension H0 x O H1 O d plus p. So you move this guy to the left hand side is equal to the dimension of H0 x O d minus dimension H1 x O d plus 1. Yeah, so you в начале имеете в виду? Ну, я имел в виду, да, то есть если одна конечномерно одна пара, то и вторая конечномерно. Нет, почему? Я не сказал. Ну, почти уже доказали. То есть then what we want? What is the conclusion? The conclusion, if Riemann-Roch is true for conclusion, or maybe I write it somewhere else. Where is? Yes, so this is Riemann-Roch. So conclusion is that if Riemann-Roch is true for OD for one of the sheaves OD or OD plus P, then it is true for the other. For the other. Yes, because in Riemann-Roch we are interested in the difference of the dimensions of the cohomology groups, and it is equal to this. And then you see when you go from D plus P, so this 1 over G is fixed, but the degree increases. So you see that yeah, if Riemann-Roch is true for OD, then it's automatically true by this equation. It's automatically true for OD plus P and conversely. And then yeah, and then Riemann then we prove Riemann-Roch by induction. By induction on the sum of the absolute values of D of X. So yeah, base. Yeah, so it is true. Yeah, so base true for D equals 0. Yeah, I already mentioned that. Yes, so if D is equal to 0, then OD is O, and then this is 1 and this is G. Yeah, so true for D, and then a step, induction step. So you write that. Any problems?
Yes, kind of. The video wasn't working already. Hopefully it works now.
Okay, you got a message from some student. Okay, so they decided to join after 50 minutes. They noticed that after 50 minutes. Okay, in the induction step, you can write that D is equal to P1 plus PM minus P1 minus Q1 minus Qn for some P1 Pi Qj in X. And then if Riemann-Roch, okay, I denote it by RR, and if Riemann-Roch is true for O, and then you write here PM minus Q1 Qn minus 1, then by this conclusion, yeah, Riemann-Roch
Которое конечное количество нулей в этом системе.
да.
Нет, но у нас в определении было сказано, что там конечное количество нулей.
Да. Ну как, берем каждую точку, соответственно. Есть конечное число точек, где функция не равна нулю, соответственно. Ну, это не полюса, это просто функция с целыми значениями d, правильно же? Ну, дивизор это просто... Да. Окей. So, yeah. So you see, yeah. So the thing is that, yeah. So again, I just repeat the whole plan. That so Riemann-Roch is true for the zero divisor. Then we do the induction on this number, and then sure. Okay, so you have D. Then let Z be the set of points such that D of x greater than 0. And Z is equal to some points, I don't know, P1, P1, P, M. And then P, 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 R, set of points. Yes. Ну, по определению D. D не равно нулю, то в конечном числе точек. Я напомню, что D это функция из x в z. Да? Вот. Значит, D это множество точек, где x меньше нуля. Окей, then D is equal. I write the decomposition. P1 D of P1 times plus P2 plus P2 D of P2 times blah 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 PM plus PM minus Q1 plus Q1 minus D of Q1 times D of Q1 times so D R is equal to Q1 Q minus D of Q1 times and blah 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 the same Qn. Yeah, fine. Okay. Yes. Yeah. So you see. Yeah. So this just briefly recall. So in general, it's with the technique that we have, the proof is simple. So we first, it's true for D equals 0, just by definition of the genus, actually. Yeah? So we define the genus in such a way that actually Riemann-Roch is true for zero divisor. Yeah, because G is just the dimension of H1. Yeah, and then you want to do the induction step. You want to prove that if it's true for OD, then it's true for OD plus P or OD minus P. And then you do it using this short exact sequence. Yes, this short exact sequence to which you apply this exact homology sequence. Okay. Какое? Ну, это же часть шага индукции, как бы. Ну как? То есть вот здесь вывод же вот какой, что здесь было conclusion, что если Рiemann-Roch верен для одного из дивизоров, то он верен для другого. То есть если эти пространства конечномерные выполнено вот это равенство, вот это, то все это выполнено для другого. Окей. Yes. So maybe just one also another I would like to probably give another corollary actually from the proof. Maybe I write it maybe here. Which is also good to understand. Just one corollary. Actually, yeah, from the proof, not exactly from the problem, from the theorem, from the proof. That dimension, so if you want to compute the dimension of H0 O d plus P, then minus dim H0 X OD. We discussed that, that this space is included in this space. But the factor is at least one dimension, so it's less or equal than 1. Yeah, okay, greater or equal to 0, less or equal than 1. Yeah, and then actually, the proof is, it's just this equation, yes. This, where is it? The first one. Yeah. Maybe I can denote it by star. Yeah. Yeah, so follows from star. From star. So when you see you increase your divisor, then the dimension of the space can increases, but not more than by 1. Okay, it's good to understand. For other application is that so for some application of Riemann-Roch, probably it becomes more powerful after we introduce third duality, but in this way it's also useful because it gives a bound for H0. So clearly Riemann-Roch implies that the dimension of X OD is greater or equal than 1 minus G plus the degree of D. Yeah, so for example, you immediately get that if the degree is big, then this space is non-empty. Yeah, so for example, if you have a positive divisor, for example, if D is equal to A1 P1 plus AN Pn, where AI are greater than 0, and sum of AIs is greater or equal to G plus 1, then the dimension of H0 of X OD is greater or equal to 2. Yes? But then what it means that? But then it implies that there exists a meromorphic function f on X such that it has such that pi so such that all the poles belong such that it can have poles only at pi, and yeah, so the order of f at it can only at pi of order and of order not more than AI. Yes. By the way, why is it important that the number is 2? For example, what is wrong if I would write here G instead of G plus 1? Then the dimension will be greater or equal than 1. What is in the problem? Yeah. Exactly, yes, because this space is at least two-dimensional, but we know that there is always a constant function, and we are not interested in constants. We know that there are always constant functions. We are interested in non-constant functions, and then yeah, so this bound gives. So you see that yeah, so we know more and more about meromorphic functions. So before we didn't know anything about meromorphic functions. Then we proved that there are meromorphic functions. But then now we know a bit more. So we know that we can control the orders of the poles. Yes, so we can say that suppose we have some points P1, Pn, A1, An. Okay, yeah, if these numbers are small and the sum of small, then, so okay, we know that there are no holomorphic functions. But then, okay, suppose we say we allow, I don't know, poles of order 1 at P1. Then it can, possibly it is not enough. Yeah, possibly there are no such functions. But then if we allow, yeah, many poles and at least G plus 1 poles, then already, yeah, we have some, yeah, non-trivial meromorphic function which has poles of order not more these numbers. Yes. Ну, это вот, да, это следствие двойственности Серра. Это мы, наверное, вот уже в следующий раз. Я ну, как бы пытаюсь сформулировать. Так, двойственность Серра, конечно, мы не докажем, но, ну, по крайней мере, в следующий раз, да. Но по крайней мере, сформулируем этот результат, да. А?
Утверждение, что род топологически равен роду геометрическому роду двойственности Серра. Вообще, для двойственности Серра это нельзя просто какой-нибудь хорошей последовательности применить.
Ну, я не знаю. Если вы догадаетесь, я был бы хорошо. Расскажите мне. Я как бы... А?
Просто в книжке написано.
Какой книжке?
В которой процедируется.
Что написано? Нет, сейчас там она, по-моему, такая... Нет, там, по-моему, вообще этого не приводится этого. А что там написано? H1.
Если верить, что да, в гомологии...
Но, подождите, но это же H1X константный пучок, правильно же? Да-да. Yeah. Yeah. The question was. So yeah. So I hope. Yeah. Next time I will explain why actually this genius that we use actually coincides with topological genius. And yeah, I said that this is a standard consequence of Serre duality. But then yeah, the question was is it whether it is possible to prove that this genius coincides with the topological genius without Serre duality? Then I don't know how to do it. So if you learn how to do it, then you can tell me. I will be happy. Первых когомологий структурного пучка, да. Вот. Ну, okay. Yeah, but by the way, for here this effect, so for n equals 1, we already knew that. We already knew that. Yeah, so you remember that we proved that there exists meromorphic function that has exactly one pole of order not more than G plus 1. Yes. So, but now we know it for several points. Yes. Okay. Yeah. Then we will now start preparation for Serre duality. So. Yeah, for Serre duality, we have to introduce now analogs of sheaves OD formed by meromorphic differentials. In the test, for simplicity, I introduced meromorphic differentials on a compact Riemann surface. So now, I introduce meromorphic differentials on any open subset. So what is the definition? Yeah, I mean, the definition is the same as for meromorphic functions. So if X is a Riemann surface, and we have an open subset, then a meromorphic differential on U is a holomorphic differential on on U without some set P, where where P in U is a discrete set, is discrete, and omega is a holomorphic differential omega on U without some set where P is discrete, and omega has poles at all points P in this set. Yes. Yes.
Constant, if it is a chart, then constant times dz, or this dz wouldn't be a meromorphic differential on u minus p.
What is what you say? What is U? U is a coordinate chart.
U is coordinate chart. P is some sort of discrete subset.
Yeah.
Then dz wouldn't be a meromorphic differential on u minus p.
No. I mean, strictly speaking, what I say, a meromorphic differential on U is a holomorphic differential on a subset of U. Yeah. So yeah, maybe where maybe it's better. Yeah, but it's the same. Is discrete. Discrete is necessarily closed, yes, by definition. Yeah. Discrete and closed. Yeah. Okay. I mean, maybe it's better to write on open subset. It's better to write like this, I think. Is a holomorphic differential on open subset such that U without U prime in U is discrete, and omega has poles at all points in the complement. I mean, it's the same, but probably just a bit nicer. Yeah. So it's a holomorphic differential on open subset such that the complement is a discrete set, and omega has poles at all points in the complement. Yeah. So dz is obviously, I mean, then U prime is equal to U. Okay. Yeah. Then. Yeah, then in the same way, so I hope the definition is clear. Then in the same way as for meromorphic functions, in the same sorry, yeah, the space of meromorphic differentials for forms, meromorphic differentials on U is denoted by M1 U. This is a vector space. Yeah, this is a vector space. Yes. Yeah, and then in the same way, as for meromorphic functions, we define the order. We define the order the order of omega at I don't know, p for or I don't know, x for any omega meromorphic form and x in U. I mean, in the same way. So yeah, so for any, if we have a meromorphic function on U, then for any point in U, we have the number, the order of this function at this point. Yeah, in the same way, we can do it for meromorphic differential. Yes, and then, oh yeah, we should probably, yeah, just introduce these sheaves. Yeah, and then what we say that. Yeah, and then in the same way we introduce sheaves omega d. So what we say that if X is a compact Riemann surface, and D is a divisor, then we define omega d of U as the set of meromorphic forms on U such that the order of omega is greater or equal than minus d of x for any x in U. Yes. Sorry? Compactness? Yeah, I said it formally. Sorry? Actually, yeah, we can define it for any Riemann surface. Yeah, I mean, this is just because we define divisors only on compact Riemann surfaces. Yeah, so yeah, so I mean, if we were, I mean, because I mean, we study actually mostly compact Riemann surfaces. So I mean, for simplicity, I introduce divisors for compact Riemann surfaces. Yeah, of course you can you introduce it for non-compact. Then you say that a divisor on any Riemann surface is a function with values in Z, such that for any compact subset, such that the support of this function, the intersection of the support of this function with any compact subset is finite. Yeah. Then this is a divisor on any Riemann surface. Okay. So these sets form in the same way as for OD, they form a sheaf denoted by obviously lambda d. Yeah, is it clear, the definition? Mhm. Okay, yeah, probably let us so that you see what we will do. I just say it's very simple, simplified third duality. Изоморфизм с чем? Не, при чем тут D'? Здесь, ну, я вообще пучки ввел. Просто у вас вопрос про что вообще? А, ну это тоже, это верно, да. Ну тоже, да. Да, мгм. Да, ну то есть тоже аналогичный факт, конечно, верен, да. I just want to, yeah, to see what is our main goal is to yeah, there is simplified third duality. It just says that the dimension of H1 XOD is equal to the dimension of H0 X omega minus D. And the dimension sorry? And the dimension of H0 X OD is equal to the dimension of H1 X omega minus D. Yeah, what is the question? What where K? Ah, yes, of course, the canonical class, you can say that omega D is equal to OD plus K. Yes. Yeah, we will also see that, yes. So, I mean, we'll explain that, yeah. So, yeah, this is simplified third duality. Why I say simplified? Because the third duality actually gives an isomorphism between this set and the dual to this set, set. There's a precise isomorphism, which is the real third duality. And yeah, I say simplified because I just claim that the dimensions are equal. Huh? Yeah, but yeah, third duality constructs precise isomorphism, some canonical isomorphism. Yeah. Canonical, yeah. So which, yeah, just without any choices, some really canonical. Okay, then we make a break. Ну, что значит естественно? Естественно означает, что если у вас есть другая Риеманова поверхность, есть изоморфизм между ними, да, то ну, индуцируется ну, изоморфизм между этими пространствами. Вот. Ну, он не зависит от выборов, короче. То есть, ну, как обычно, да, то есть он хорошо себя ведет при изоморфизмах объектов, да. Ну вот вы, наверное, потому что это физику изучали, да, то есть вас не учили, да, что V и V со звездочкой не канонически изоморфны, а V и V с двумя звездочками канонические. Знаете это, да? А? Ну, да. Ну, это как бы важно, потому что, ну, эти вопросы важны, если вы как бы это, ну, рассматриваете семейство, потому что, ну, так, люди еще рассматривают пространство, семейство, ну, например, семейство римных поверхностей, и тогда как бы, ну, если у вас какой-то канонический изоморфизм, вы получаете, ну, понимаете, если у вас есть там семейство римных поверхностей, то эти группы когмологии задают какое-то расслоение, и если у вас есть канонический изоморфизм, у вас получается изоморфизм векторных расслоений. А если что-то не каноническое, то вы ничего не знаете. Вот. То есть, ну, это как бы важно в вопросах, как бы, когда рассматривается семейство объектов. Ну хорошо, там мы сделаем перерыв 5-минутный. We get 5 minutes break. But if you, то есть если вы не получаете рассылку, вы, получается, ничего не знаете про экзамен вообще, да? Да. Ну, как же, это очень важно. То есть, а? Да-да. То есть у нас как получается? Ну, оставшиеся они точно в рассылке? Ну, я надеюсь. То есть вы получаете рассылку, да? Do you get messages about lecture notes, about exam? So, did you receive my message about exam? Окей. То есть, ну, да. То есть у нас что получается, какие тут правила вышки, да, что, ну, как раз вы же, получается, третий курс, да, ну, то есть у нас, получается, четвертые бакалавры и второй год магистры, у них, получается, экзамен 25 мая. Ну и, кстати, да, чтобы вот успеть рассказать про двойственность серы поподробнее, у нас будет дополнительная лекция. Ну вот, ну, следующий вторник, да? 23 мая. 23 мая. Ну да, в то же время, то есть получается в 13:20, 16:10, аудитория, комната 318. Вот, значит, вот. Экзамен, значит, только для четвертых бакалавров и второго года магистров, а все остальные, то есть, да, то есть не эти, значит, продолжают. У нас, получается, будет лекция 1 июня. 1 июня. Ну вот 8 я буду в отъезде. Значит, 15 июня. Вот. И уже экзамен. Экзамен, ну, собственно, неделю, 22 июня. Лекция-семинар. Ну, вот я говорю, с 13:20 до 16 есть лекция-семинар. Да-да. Да-да. Ну да, лучше сказать дополнительная лекция и семинар. А? У вас какая-то другая еще пара в это время, что ли? Механик? О, да. Ну ладно. Странно, получается, другие, что ли, тоже так? В принципе, ну, я обсуждал у нас в учебной части, куда назначить. Раз я была надежда, что это не пересекается ни с чем. А? Да. Ну ладно. Сейчас? А? Мгм. Да. Ну что ж, ну давайте еще, да, сейчас через 3 минуты мы начнем. So about hyperelliptic curve. So what we discussed last time, we discussed that so last time we considered the curve y squared is equal to qx in C2. And then we showed that it is possible to add 2 points, x bar, x union. We denoted these 2 additional points by plus minus infinity. And then so we added 2 points and introduced a complex structure on the resulting space and get a compact Riemann surface. And this is a hyperelliptic curve. Hyperelliptic Riemann surface. Yes. Yes, and then we also discussed these holomorphic differentials on x. So maybe I repeat that. Yeah. So first, x to the power I, y to the power j dx is holomorphic on x. Yeah, if and only if. There are 2 cases. So if I greater or equal to 0, j greater or equal to 1, in the case xi is not equal to 0 for any I. Yeah, so q of x is the product x minus xi. I equals 1 to 2g plus 2. Yeah, this is just recall what we did on the previous exercise class. Yes, and then or 2i plus g greater or equal to minus 1 and g greater or equal to minus 1 in the case xi equals 0 for some I. And then we finished by discussing what happens on x bar, on the whole hyperelliptic curve. So we said that in this case, xi is not equal to 0 for any I. What we have? xi y to the power j dx is holomorphic on x bar on the whole. If and only if j is equal to minus 1 and I greater or equal to 0, less or equal than j minus 1. Yeah, so you get that. Yeah, so only I dx over y I. So only these differentials are holomorphic on x bar. And actually, surprisingly, in the second case, the answer is the same. Yeah, it's a simple. It's simple computations. I don't do it, just for your information. Yeah. actually in the case xi equals 0 for some I, the answer is the same. The answer for x bar is the same. Meaning that, again, xy y to the power j dx is holomorphic on x bar if and only if I greater or equal to 0, less or equal than g minus 1, and j equals minus 1. Yes. Yeah, actually, it's just arithmetic computation. So this condition, together with the condition at infinity that you get, imply the same constraints. Okay. Okay. Are there any questions? Okay, if there are no questions, then we should discuss yeah, we should discuss applications of actually short exact sequences, because it's one of the main tools to compute cohomology groups. Yeah. For example, okay, I guess you know the definition of the Dirac cohomology. Yeah, so we have the sequence of so if X is a smooth manifold. Нет, а как же, мы же это считали. Мы же считали поведение на бесконечности, то есть мы вот взяли этот дифференциал, ну точнее вот уже взяли вот это ограничение, а дальше посмотрели, когда он голоморфен в точках на бесконечности. Вот. И там у этого возникло это ограничение. Да. Не рассматривали? Ну, что-то мы это рассмотрели. Okay, we can discuss it. I mean, it's fine. Okay. We can do the second case, for example. Does anybody want to do that?
The coordinate there is x at infinity.
At infinity?
Well, 1 over x.
Yes, yes. Yeah. Do you want to do it? Okay. But okay, we can make this computation. Yeah? Do you want? Так сказать, повторение, мать учения. Вот. Mm-hmm. Yeah.
Then I guess you want to say that x is 1 over w and y is okay, first just change x and then y will be some function of w and get back to this.
Mm-hmm.
So yeah, we have I can write it. Y is
Mm-hmm.
And now I want to compute y.
It's minus, strictly speaking, yes. Yeah, strictly speaking, minus, yes. Dx, I mean, when you take d of 1 over w, I mean, you get minus, yeah, I mean.
Yeah, and now we want to evaluate y as a function of w.
Mm.
So we say that y squared is u 1 over w. And
Mm-hmm.
well, let's take derivative, right, with respect to y.
How? Okay, you can do it, but you want to express y as a function of w. So
Yeah.
how does it help you to express?
Well, I want to use the implicit function theorem, possibly.
Okay, to be honest, I'm a bit frightened by this plan. I mean, but we did that. What you can do. Q of 1 over w is the product 1 over w minus xi. You can put it outside w 2g plus 2 product 1 minus xi w. And then, I mean, when w is small, you can take square root, and here you can also take square root. Yeah.
That means that this thing is
Yeah.
okay. Yeah, and then this is one over minus h of w y plus I plus g j plus j, right?
Mm-hmm.
No, it's not true. Plus 2.
Yeah.
And then we want I plus gj plus j plus 2 greater or equal than 0. No, less or equal than 0. And we're dealing with the case, with which case?
The second case, yeah, this one.
Okay. Well, anyways, I guess you have that.
Yeah, I mean, you can. I mean,
Okay,
let us just
greater than 0 anyways, right?
No. We are go working the second case where you have just these two conditions: 2i plus j greater or equal than minus 1, and j greater or equal than minus 1.
Well, then 2i is equal to minus j minus 1.
Not equal. I mean, greater or equal. Yeah.
And j is minus 1, so minus j minus 1 is 0, right?
Yes.
So in both cases, I is greater than 0. Isn't it true?
No. You see how you get it? 2i greater or equal than minus j minus 1. And then what?
Yeah.
You see, j can be big and I can be negative. Yeah.
Okay, yeah. Then I might have a problem here.
Yeah, actually, you can. What you can do? You can. Yeah, I think you can. Yeah, write with. With minus. And then write 2i plus j greater or equal than minus 1, and then multiply by 2 and sum with here. So to exclude I, to exclude I. Formally speaking, minus j, you're right. Okay, okay.
Okay, then this whole thing is less or equal than right?
Yeah, I mean, I suggested just to sum this and this. Yeah. Multiply this by 2 and sum with this.
Yeah. This is eruit. Well, that's what that makes it minus 2 gj minus j minus 4 greater or equal. No, bigger than minus 1.
Mm-hmm.
That's true, yeah.
Yeah. Yeah.
Right?
Yes.
Well, and if g is greater or equal than this is anyways strictly less than 0.
Yeah. Yeah, but you also have condition j greater or equal than minus 1, yeah?
Yes, yeah, that's where I was going for. Yeah, when this in case when g is equal to 0, that means that this form cannot be homomorphic at all.
Yeah, indeed.
And in case when g is greater than 0, I mean we have this is a sphere and not a projective plane, it's fine. And then j is equal to minus 1. So and then I guess I should switch to the other.
Yeah.
So then it should be that way. It should
Yeah, this is fine.
the same for different g's.
Yeah. Yeah.
In this case, j is equal to minus 1. And to apply to j, and then to I is greater or equal than. So then on one hand, I is greater or equal than 0.
Yeah.
And on the other hand, so it's g plus 1, so minus a plus g plus 1 is.
Yeah. No, you see, G minus 1, so this is G plus 1 minus 2. So okay, I greater or less or equal than G minus 1. Okay, this is the same thing. Okay, yeah, so we get the same thing, yeah. Okay, thanks. Are there any questions? Sorry? Ah, yeah. Yes. Yeah, well, formally this case is also good because then I should be less or equal than minus 1, so empty condition, yeah. So, so yeah. So in general, there's the same answer, yeah. Okay. Then I want to discuss applications of short exact sequences. Yeah. For the first one is relation with the Ram cohomology. So recall of the Ram cohomology. Yeah. So the Ram cohomology. So what is that? We have X smooth manifold. And we have differential forms. We denoted the sheaf of differential forms by epsilon and index d. Epsilon n x d epsilon n plus 1 x. And then h n, okay, the Ram x is defined as the quotient of the kernel of d from epsilon n x to epsilon n plus 1 x by the image d epsilon n minus 1 x yeah, so this is standard. And then so problem prove that h1 of x, the sheaf of locally constant functions with values in C, is isomorphic to h1 the Ram. The Ram x. Yeah. I guess you studied the Ram cohomology in the course of analysis on manifolds. Then it occurs that this is true. So how to prove it? I said that, by the way, yeah, so again, this is the first cohomology of the sheaf of locally constant functions with values in C. This is the Ram cohomology. Sorry? Нет, все правильно. Для омега у нас были голоморфные формы, да, а эпсилон мы обозначали, соответственно, гладкие функции и гладкие формы комплексно значные. Yes. So smooth differential forms with coefficients in C. Yeah, so you remember. So yeah, I said that this is an exercise for exact cohomology sequence. So one should write some short exact sequence. What are short exact sequences? So I just recall a definition. So what is that? This is the kernel of D from epsilon 1 to epsilon 2 x divided by the image D from epsilon x, just smooth functions, to epsilon 1 x. So if we want to use it, so to prove it using exact sequence and cohomology, one has to write some short exact sequence involving this sheaf and the sheaf of smooth functions. What is the sequence? Okay. Idea. So you want to write C, D, epsilon, and epsilon 1? Yes? But is it exact? Sorry? No. What about here?
Well, every point has in a simply connected neighborhood. Yes. And there, I guess, differential forms. Yeah. This one differential form is all closed ones are bound.
No, then here you have all forms. Yeah. So. So I mean, only closed form is so you define. We define Z1 as the sheaf of closed one forms on X. And then indeed you can write Z1 yeah, then okay, so you have indeed you have differential. So then locally constant functions are obviously smooth, so this is inclusion. And here, of course, I mean, if the differential of a function is 0, I mean, the function is locally constant if and only if its differential is 0. So the exactness here is also clear. Okay, what about here? I mean, okay, locally, any closed form is exact. So it's d of some function. So, I mean, by Poincaré lemma, I mean, we have exactness here. So this is exact sequence. Yeah, is it clear? And what then? Yeah, yeah. So then you write exact cohomology sequence. Zero. Okay, we can write C. Oh, no. Yeah, strictly speaking, our manifold can be not connected, so we should write X C epsilon of X Z1 of X H1 of X C and H1 of X epsilon. And then remember that we proved that the first cohomology group of the sheaf of smooth functions is 0. Yeah. So, but then, so this space is 0. But then it means that this space is the quotient of this guy by the image of this guy. Yeah. 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 So I don't know if we denote it. Yeah, maybe let us denote it by beta. Then using our notations, this is beta 0. Yeah, then H1 is isomorphic to Z1 X quotient by the image of beta 0. Yeah, yeah. This is exactly H1. There yes. Are there any questions?
Is it a simple higher dimension?
Yeah, it's also not hard. Huh? Да. Да-да. Но ведь вот точность-то понимается в локальном смысле, да? То есть что, ну, да. А? Ну, конечно, ну как, ну это же есть дифференциал. Ну, в принципе, да. То есть, действительно, как бы, I mean, it's not as quick, but also not hard. Yeah. So in general, of course, we have a fact that a remark that in general we have that, of course, H1 XC is H1 deram. Yeah. Yeah, I mean, it's not hard, but yeah, it takes some time. Yeah, I mean, if I remember correctly, the idea is to consider, I mean, they consider a family of sheaves. They consider yeah, so I think the idea is to consider something like the sheaves H. Okay, anyway. Okay, so what else? What are other applications? I think also, yeah, a nice application. I mean, classification of linear vector bundles. Vector, the space, the set of isomorphism classes, the set of isomorphism classes of the set of isomorphism classes of rank 1 vector rank 1 complex vector invertible functions. Okay, and then now the problem is that if X is paracompact, so no, not a bad space. If X paracompact, then this is actually isomorphic to something more understandable. This is H2 XC. H2 X C. XC. Yeah, to be honest. Yeah, I mean, sorry, maybe it's okay. It's of course true, but probably we can prove it for smooth manifold again. X is a smooth manifold. Then yes. Yeah, so actually the set of isomorphism classes of rank 1 complex vector bundles is isomorphic to H2XC. No, sorry. Again, H2XZ. Sorry. Z.
Did you prove that the homology of continuous functions is 0?
But I mean, the proof is the same. I mean, again, you use.
I just need to say the short X sequence then, right?
Yeah.
So it's the exponential
Mm-hmm.
short X sequence, right?
Yeah. So. So yeah, so indeed solution is then you write short exact sequence short exact sequence 0 Z continuous functions, and then you take exponential 2 pi I times C star. Yes. Yeah, and then you write exact sequence, exact homology sequence. That part with H1. Yeah. So you write H1 X C. H1 of X C star. This is what we are interested in. Here you write H2 X Z. H2 X C. Yes, and then you just note that this is 0 and this is 0. Yeah, I mean, formally we proved it for smooth functions, but for continuous is the same. So I mean, just literally the same. You just use this partition of unity, and then you get what you want. Yeah. So the same proof as for the sheaf of smooth functions. But this is true for paracompact, because on paracompact spaces you have continuous partition of unity. Yeah. Okay. Are there any questions? Actually, maybe again a nice remark. Here at this moment there are many beautiful things. Ну вот я как раз хотел сказать. Ну это, ну, кстати, в этом случае... Ну, кстати, да, здесь тоже работает. Ну, окей. So, remark. So, you get an isomorphism. Okay, so we get... so if L over X is a rank 1 complex vector bundle, then so I think we denoted by psi, yeah. No, I think we just said psi is a rank 1 complex vector bundle over X over X. Then what we know, to X we assign да. То есть then we know that I think we use this notation. We assigned to psi the cohomology class H1 X C star. And so we get that this is isomorphism. We denote it by delta 1. And then H1, and then you map it by delta 1, I mean this delta 1, to the element H2 X Z. Yes. So this is how we, so we get the some bijection with set of isomorphism classes of rank 1 complex vector bundles and H2. So you get some. So you see it is constructed using I mean this procedure. So it's first so it was some homework. So by homework you assign to psi some element is in H1 X C star, and then this is also some procedure, some delta 1. You want, of course, I'm not sure that you remember how it works. I mean, but then the question how to describe this assignment directly. And this is actually a beautiful result that this is the first Chern class. So this assignment from psi to this is the first Chern class, just C1. You to psi, you assign C1 of psi. The first Chern class. Chern class of X, of psi. Okay. So there is a beautiful description of this composition. Okay.
There is nothing of this kind for real numbers. Yeah.
For real numbers. No. One can. So if you consider real. I mean, how to describe the set of isomorphism classes of what? What do you want? Just real rank one vector bundles? Ah, but it's indeed it's just. I mean, it's also simple. It's just because real. Probably I can't say immediately, but this will also be something like a cohomology group with Z2 coefficients, something like this. Because I mean, yeah, computation. Because a real vector bundle is more or less the same as a covering, a degree 2 covering. Yeah, and then. Yeah, I think he's right. Yeah, so I think it's classified by the first Stiefel-Whitney class. Yeah, I think yes. Yeah, a real rank one. Yes, I think something like this. Yeah. Не, ну это результат, ну какое-то вычисление не вполне тривиальное, да, но это надо доказывать. Ну, как бы, не, ну это не, ну это не, я как бы как ремарка, да, то есть, но это совершенно как бы, ну такой неочевидный результат, довольно, в общем-то, красивый. Но это все делается как бы в топологии же как, есть же общий результат вообще, что любое векторное расслоение, ну над достаточно хорошим пространством, оно получается обратным образом тавтологическое расслоение над Гроссманианом, да? Поэтому как бы все это можно достаточно проверить над Гроссманианом, где это, ну, в принципе, какая-то прямая проверка более-менее. Да. Ну да. Ну, в общем. Окей. Yeah, again, maybe one more exercise on. So the idea is that we studied some short exact sequences, and you can try to apply this exact cohomology sequence to each of it, and get something interesting. Yeah, for example, another thing that one should probably understand. How to compute this H1XO in terms of differential forms. Yeah, so X is a Riemann surface. Then we have H1 XO is isomorphic to the differential forms of type 0, 1 quotient by the image of smooth functions. Yeah, so okay, maybe I write it in the way I d double prime epsilon x. Yeah. So here, this is about now Riemann surface. No, it's not with smooth coefficients. So when I write epsilon 0, 1, it means locally of the form f dz bar, where f is smooth. Yeah. Hmm? Yeah. Yes. So again, so solution. Again, short exact sequence. Short exact sequence 0 O. So holomorphic functions, they are inside smooth functions, and then you apply d double prime and get epsilon 0 1. Yes. So the exactness here obvious. So exactness here, yeah, obvious. Just inclusion. Yeah, here. I mean, just by definition of holomorphic function, that a smooth function is holomorphic if and only if df over dz bar is equal to 0. So, and yeah, it is exactly what this says. Yeah, and then here, yeah, yes. So that here it follows from the fact that any function, any smooth, any f smooth function on a smooth function on C is locally f is equal to dg over dz bar. Yeah, where g is smooth. G is smooth. So yeah. So we proved that for any smooth function on a disk, it is equal to dg over dz bar, where g is a function on this disk. Yeah. Yes, and then you apply, yes, and then you write exact cohomology sequence, exact cohomology sequence, exact cohomology sequence, and so you get we are interested in this h1. So okay, so you write the place this h1 xo, then it maps to h1 x epsilon, which is 0. We know that the sheaf of smooth functions has 0. Yes, then here h1, here you have h0 x, so actually sections, smooth functions, and here you have epsilon 0 1 of x. Yeah, and then yeah, here you get O x, but I mean this is not important. Yeah, so and exactly since this is 0, h1x epsilon, then it means that h1 xo is epsilon 0 1 of x quotient by the image of epsilon x. Yes. Okay. Okay. Ну, сейчас, прямо для этого я что-то сейчас прямо, наверное, сразу не вспомню, как это перекладывается. Но есть немножко другая, которая вот для двойственности сервера будет играть. Окей, maybe actually it's good that you say that. Maybe another problem that actually will be used in Serre duality. H1, what is it? Yeah, so prove that, again, X Riemann surface. Then H1. So I write immediately then important for Serre duality. For Serre duality. Then H1 of X epsilon omega is isomorphic to epsilon 2 forms on X quotient I guess the image of D epsilon 1 0 of X to epsilon 2 of X. Yes. Yes, exactly. Or you can write, I don't know, you can write. Yeah, I mean, this is, yeah, at least this is clear. Yeah, I mean, the formulation, yeah. That if you apply differential to a form of type 1, 0, you get, yeah, I mean, it's obvious, yeah. I mean, differential of any one form, you get a 2 form. And then the space of 2 forms on X, quotient by the image of this guy, is isomorphic to each one X holomorphic forms. Yeah. So what should we write? Yeah, yeah, of course. Yes, yes. So short exact sequence, so solution. Short exact sequence. Short exact sequence 0 omega epsilon 1 0 and epsilon 2. Yeah, and again, I mean, this is here. This is just inclusion, and then yeah, again. So since an element here is f dz dz, yeah, where f is smooth, then d of this guy is equal to df dz bar dz. So the differential of this guy is 0 if and only if f is holomorphic. Yeah, so this proves the exactness at this place. And the exactness here is again follows from this fact that locally any function is d over dz bar of some function. Yeah. So you write this short exact sequence, and again write cohomology. Yeah, so exact cohomology sequence. Exact cohomology sequence. So we are interested in H1. Yeah, so you write epsilon 0 1 of X. This is delta 0. You write H1 of X omega. And then you should write H1 of X omega 1 0. But then again, this is 0. This is 0, and the proof is the same as for smooth functions. The smooth functions, same proof as for epsilon. Yeah, you can remember that in that proof we choose some representative just some representative, and then using partition of unity proved then that this cocycle that represents a cohomology class here is a coboundary. And there we use the partition of unity, then we just have to construct partition of unity, multiply it by its elements, the elements of this sheaf. Okay, and then you can do it for also for differential forms. So this is fine. Okay, so and then you get exactly what is needed here. That since this is 0, then this space is the quotient of this by the image of this. So 1 0. Sorry, it's 1 0. Yes, 1 0. Okay. Yes. Okay. Okay. Yes. Any questions about this? Okay. If there are no questions, then we can probably try to compute some, since we have some time. So we studied the sheaf OD. Let us but okay, probably okay. We will prove that the genius coincides with topological genius, but even before that, okay, we know that. So we know that G of CP1 is equal to 0. Then okay, this is because so we at some moment we computed that CP1 O is equal to 0. It was from the first test. But actually it's easy to prove the converse. So prove that. So suppose X is a compact Riemann surface, and G of X is equal to 0. Prove that X is isomorphic to CP1. How to prove that?
Well, it's something to do with one of the last statements we proved during the lecture, right? We just choose a meromorphic function and it has goals at more than G plus 1.
Yeah. So indeed the proof is simple. So we know that. So solution that from the lecture. So there exists meromorphic function on meromorphic function f from X to CP1 with only one pole of order okay, less or equal than g of x plus 1, but since g of x is equal to 0, so you get that order is equal to 1. But then f is a biholomorphism. But then f is a biholomorphism. Yes. So x is yeah. Yes. Yeah, because we proved that. So if there is only one pole of order 1, then the degree of this map is 1. So and we proved that then the sum of the preimages, the multiplicities of the preimages of any point in CP1 is equal to the degree. But okay, but then it means that for any point in CP1 there is only one preimage. So there is inverse map and it's also holomorphic. Okay. Okay, maybe at this just a remark. Okay, we in this course we will not prove that, but these are standard results that any compact. Okay, suppose X compact Riemann surface. Compact Riemann surface. Then, yeah, I mean the first if g of x is equal to 1, then x is isomorphic to a complex torus. And second, in Genius 2 also, the description is nice. Then it's hyperelliptic. Then x is isomorphic to hyperelliptic curve. Elliptic curve. Yes. But then, okay, if g is higher, then of course they become more complicated. Okay, but we will not be able to prove it. Okay. Что? Ну, я говорю, не будем, нет, ну, не успеем уже. Ну, не, ну, в принципе, это на самом деле не сложно, как бы, ну, просто как бы надо аккуратно это сделать. Ну, то есть, фактически, что такое гиперэллиптическая кривая? I mean, actually, the idea is simple here. You can, I mean, yeah, for complex torus, it's actually simple, just a bit technical. I mean, you can remember what? No, actually, yeah. Ну нет, это же вопрос про комплексную структуру, как бы, вот, что, ну, как бы комплексная структура берется только вот из такой конструкции, которую мы как бы описывали. I mean, hyperelliptic curves are exactly curves of, so we remember that hyperelliptic curve has a map to CP1, so of degree 2. And actually, hyperelliptic curves are exactly Riemann surfaces, compact Riemann surfaces that have degree 2 map to CP1. And then actually, I mean, here in the first part, how to prove it? If G is equal, then one first has to prove that a complex torus is hyperelliptic, and then one can note that any Riemann surface of genus 1 has a function, has a meromorphic function of degree 2, which is a Weierstrass P function. And then it's hyperelliptic, and then, okay, one has to prove that any hyperelliptic curve of genus 1 is actually a complex torus. Okay, I mean, it's quite technical. And here means, okay, I mean, again, here it's similar, so one has to find meromorphic function of degree 2. Okay, there is some work. So we will not be able to prove it. But okay, maybe there is not much time left, so probably we finish for today.